Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the essay, 1763. Thomas Bayes, an essay towards solving a problem in the doctrine of chances, a cornerstone of probabilistic reasoning, stands as a testament to the power of inductive inference. Its legacy extends far beyond the confines of probability theory, shaping fields from statistics and machine learning to artificial intelligence and philosophical inquiry. The essay, posthumously published by Richard Price, Bayes' friend and champion, offered a novel approach to inferring probabilities from observed data, a problem that had previously eluded satisfactory resolution. To fully appreciate the significance of Bayes' contribution, one must first understand the intellectual landscape from which it emerged. The doctrine of chances, as it was then understood, was experiencing a period of heightened activity. Before Bayes, figures such as Christian Huygens, Jacob Bernoulli, and Abraham de Moivre had laid crucial groundwork. Huygens, in his 1657 treatise on games of chance, established early formulations of probability. Bernoulli, with his ars conjectandi of 1713, provided the law of large numbers, a fundamental theorem linking relative frequencies to probabilities. De Moivre, a pivotal influence on Bayes, refined these concepts, providing a first formal treatment of the normal distribution, crucial to understanding data. De Moivre's The Doctrine of Chances, a text of profound influence, directly addressed probability calculations. His work, providing techniques for calculating probabilities in various scenarios, formed a necessary point of departure for Bayes. Bayes built upon this foundation, seeking to solve a problem addressed by De Moivre, but remaining unresolved how to reason from observed effects back to their underlying causes. Central to Bayes' essay is the articulation of a method for calculating the probability of a hypothesis given the evidence. This is achieved through what is now known as Bayes' theorem. The theorem provides a mathematical framework for updating beliefs in light of observing new data. The essence of the theorem lies in the interplay of three key probabilities: the prior probability, the likelihood, and the posterior probability. The prior, representing one's initial belief in a hypothesis before observing any data, is integrated with the likelihood. The likelihood quantifies how well the observed data supports the hypothesis. The posterior, representing the updated belief after seeing the data, reflects the combined influence of the prior and the likelihood. To state this mathematically, in full spoken form, the posterior probability of a hypothesis given the data is equal to the prior probability of the hypothesis multiplied by the likelihood of the data given the hypothesis, divided by the marginal likelihood of the Bayes illustrated his method using a specific problem. He posed a scenario involving a biased billiard ball rolling on a perfectly smooth table. The ball is rolled, and the position where it lands is observed. With the initial position of the ball unknown, subsequent balls roll onto the table, and the positions of these balls are observed. Bayes' goal was to determine the probability that an unknown ball will come to rest in a particular segment of the table. He used a geometric argument to describe the probabilities. He imagined the table as the unity interval and the probability of an event as a linear function of the position of the ball. The observed positions of the balls provide information, and the analysis provides a way to combine these observations to determine the probability. This methodical geometric argument exemplifies his approach. Bayes' proof has been lauded for its elegance and mathematical ingenuity. He utilized the principles of probability in a creative manner. He employed the concept of conditional probability and the rule of conditional probabilities, crucial concepts for developing a modern understanding of statistical inference. In his seminal work, he rigorously established a process for inferring an unknown probability from observed data, a concept that had far-reaching implications. This framework laid the groundwork for what we now term Bayesian inference, a cornerstone of modern statistical analysis. The immediate impact of Bayes' essay resided in the domain of probability and statistics, but its implications reached beyond. For instance, Price's foreword to the essay served as a means of introducing the principles of insurance and annuity calculations. This application of Bayes' method to practical problems demonstrated its utility. This early application, although perhaps not immediately revolutionizing these fields, demonstrated the practical application of the underlying theory. In particular, the method began to be used to analyze the accuracy of observations and assess the reliability of evidence, an important concept for scientific The reception of Bayes' work was initially muted. The essay's publication was followed by a period of relative obscurity. De Moivre, although a significant influence, did not immediately recognize the profound implications of the theorem. However, the theoretical framework was later embraced by mathematicians and statisticians, particularly during the late 19th and early 20th centuries. As statistical methods developed, the importance of Bayes' work became progressively apparent. The subsequent evolution of Bayesian methods involved refinements and generalizations. Pierre-Simon Laplace, a towering figure in mathematical physics and probability theory, independently rediscovered and extended Bayes' theorem. Laplace developed a more systematic approach, applying it to celestial mechanics, error analysis, and inverse probability problems. Laplace's emphasis on Bayesian methods helped establish the importance of Bayesian inference, and he made significant contributions to generalizing the theorem. He formalized the method. Laplace's work brought the method into the mainstream of mathematical statistics, solidifying its significance. The early 20th century witnessed a period of competing schools of statistical thought: classical or frequentist statistics, emphasizing the frequency of events, was dominant, and Bayesian methods faced challenges due to issues concerning the selection of prior probabilities and computational complexities. Despite such competing influences, Bayesian ideas persisted, particularly in the areas of engineering and military applications. Later, developments in computing made complex calculations feasible, leading to a resurgence in Bayesian approaches. The second half of the 20th century saw a renaissance of Bayesian statistics. This renewed interest was fueled by the development of high-speed digital computers, facilitating complex calculations. The computational capacity allowed scientists to apply Bayesian methods to a range of previously intractable problems. The advent of Markov chain Monte Carlo methods, a class of algorithms for sampling from complex probability distributions, provided powerful tools for performing Bayesian inference. Researchers discovered that Bayesian methods offered a natural framework for modeling uncertainty and incorporating prior knowledge, especially valuable for experimental sciences and complex decision-making. The impact of Bayes' work extends to numerous modern fields. In scientific research, Bayesian methods allow researchers to update their beliefs based on experimental evidence. They facilitate the incorporation of prior knowledge into the analysis, allowing researchers to interpret data. In machine learning, Bayesian methods are at the forefront of many algorithms, from classification and regression to natural language processing and computer vision. The ability to learn from data while incorporating prior beliefs is a powerful feature. Bayesian networks, which are graphical models that represent probabilistic relationships between variables, are employed in artificial intelligence and decision-making systems. Bayesian methods contribute to risk analysis, financial modeling, and other areas regarding direct influences. As mentioned earlier, Tomoeva and his doctrine of chances exerted a considerable impact on Bayes' work. Bayes drew upon the mathematical techniques and conceptual frameworks established by Tomoeva. The problem Bayes sought to solve stemmed directly from Tomoeva's work, indicating a clear intellectual lineage. Additionally, Bayes' affiliation with the Royal Society indicates exposure to the scientific community and its ongoing discussions, which may have facilitated his work. Price played a crucial role in sharing Bayes' work after his death, demonstrating their friendship and professional connection. Bayes' influence permeated many areas of scientific and technological study, resulting in diverse applications. Laplace's work, which built upon Bayes' foundation, demonstrated the importance of inverse probability. The subsequent application of Bayes' work in the field of insurance and annuity calculations, as Price demonstrated, reveals the practical value of the method. The impact of Bayesian inference on the development of artificial intelligence and machine learning algorithms represents a contemporary direct influence. The utilization of Bayesian methods in medical diagnostics and other fields further reflects controversies surrounding Bayesian methods involve the choice of prior probabilities. Different choices can lead to different posterior distributions, leading to debates about the objectivity of the methodology. Critics argued that the selection of a prior inevitably injects subjective beliefs into the analysis. This challenge spurred considerable discussion, leading to methods for making more objective choices about priors, such as the use of vague or non-informative priors and techniques for assessing the sensitivity of results to different prior assumptions. Despite these debates, the fundamental concepts established by Bayes have remained the cornerstone of this framework. In conclusion, Thomas Bayes' essay towards solving a problem in the doctrine of chances provided a groundbreaking framework for inductive inference. Bayes' work, starting from the foundations laid by earlier mathematicians, developed a method for updating beliefs in the light of new evidence. The application of Bayes' theorem extends far beyond the original context of probability theory. Its methods and principles, refined by generations of researchers, are now indispensable tools for scientific inquiry, machine learning, and other fields. The enduring legacy of Bayes lies in the power of his approach to quantify uncertainty and reason from data. He gifted us with a framework for rational inquiry, forever changing how we understand and interpret the world around us.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.